Bismillahirrahmanirrahim. I'm your physics teacher, Miss Kiran Shehzadi. Let's start today's lecture. Uncertainties. In any measured value, there is a degree of inaccuracy. This may be due to limitations in the equipment, measurements, or due to experimental procedure. Uncertainty means the range of possible values within which the true value of the measurement lies. How do we indicate uncertainties in a measurement? Let's understand it by the help of an example. In an experiment, the length of block is measured with a meter rod and it is found to be 22.5 centimeter. One end, represented by A, coincides with 10.5 centimeter mark and the other end, represented by B, coincides with 33.0 centimeter mark. Calculate the percentage uncertainty. We have this block and length of this block is calculated by the help of this meter rod, and A of this block coincides with 10.5 centimeter mark and B end of this block coincides with 33.0 centimeter mark. So by subtracting 33.0 and 10.5 we get 22.5 centimeter. So 22.5 centimeter is our measured value. As the least count of the meter rod is zero point 0.1 centimeter, therefore total uncertainty in the measured value will be plus minus zero point 0.1 centimeter. We write uncertainty with plus minus sign because the total uncertainty in this experiment is plus minus zero point 0.1. So plus minus 0.05 centimeter uncertainty develops at one end and plus minus 0.05 uncertainty develops at the other end of the block. In total, the magnitude of uncertainty will be equal to plus minus zero point 0.1 centimeter. Length of the block with uncertainty is given by 33.0 plus minus 0.05 centimeter minus 10.5 plus minus 0.05 centimeter. Because for calculating length of this block we subtract two values 33.0 and 10.5, but for calculating uncertainty in the measurement we write these values with uncertainty. As we discussed that total uncertainty in this experiment is plus minus 0 0.1 centimeter, that is the least count of the measuring scale. So half of the uncertainty develops at one end A and another develops at one end B. So we'll write 33.0 with plus minus 0.05 the uncertainty at point B, and we write 10.5 with plus minus 0.05 the uncertainty at point A. By subtracting we get 22.5 plus minus 0.1 centimeter. Here 22.5 is our measured value and plus minus 0.1 is absolute uncertainty or least count. So this least count or absolute uncertainty can be added or subtracted in our measured value to get the range of possible values within which the true value of the measurement lies. When we subtract it, we get 22.4 centimeter, and when we add 22.5 plus zero point 0.1 we get 22.6 centimeters. So length of the block is in between 22.4 centimeter to 22.6 centimeter. In this measurement, least count or uncertainty or the magnitude of uncertainty is equals to plus minus 0 0.1. Remember that least count represents uncertainty or magnitude of uncertainty in a measurement. Hence, precision is equals to plus minus 0 0.1 centimeter. As the precision is also guessed from the uncertainty in a measurement, that's why we write precision is equals to plus minus 0 0.1 centimeter, that is the least count or absolute uncertainty of the measurement. Formula of the magnitude of relative or fractional error is equals to least count or uncertainty or absolute uncertainty or magnitude of uncertainty divided by measured value. In our this experiment, least count or magnitude of uncertainty or absolute uncertainty is equals to plus minus zero point 0.1 and the measured value is 25.5 centimeters. By putting the values and dividing, we get the magnitude of relative error or magnitude of fractional error that is equals to plus minus 0.004. We can define accuracy in our measurement by the help of magnitude of relative or fractional error. So this magnitude of relative or fractional error is equals to accuracy in this measurement. And we get accuracy is equals to plus minus 0.004, that is fractional error. Remember that smaller the magnitude of relative error, greater will be the accuracy in the measurement. Formula of percentage uncertainty is equals to magnitude of fractional error multiplied by 100%. For finding percentage uncertainty, we just multiply our relative or fractional error by 100%. In this experiment, percentage uncertainty is equals to 0.1 divided by 25.5 multiplied by 100% and we get 0.4%. Let's see another example. Another measurement taken by vernier calipers with least count 0.01 cm is recorded as 0.4 cm. Calculate percentage uncertainty in it. Solution. As we know that precision or absolute uncertainty or magnitude of uncertainty is the least count of the measuring instrument, that is equals to plus minus 0.01 cm. As we know that formula of fractional uncertainty is equals to least count divided by measured value. By the putting values, we get 0.01 divided by 0.45 and after solving this we get fractional uncertainty is equals to 0.02. For finding percentage uncertainty, we just multiply fractional uncertainty by 100% and then we get 2.0%. So fractional uncertainty is multiplied by 100% and then we get percentage uncertainty is equals to 2%, 2.0% in this experiment. Calculating uncertainty in the final result. After experiments, we do calculation, and in calculations, sometimes we add or subtract measured values, sometimes we multiply or divide our measured values, sometimes quantity contains power, sometimes we take average of our measurements. So we apply rules to calculate uncertainty in the final result. Let's see an example. The distance x determined by the difference between two separate position measurements. If x1 is equal to 10.5 with uncertainty plus minus zero point 0.1 centimeter and x2 is equal to 26.8 with uncertainty in it plus minus 0.1 centimeter. For calculating the distance between these two positions, we subtract these, and for calculating uncertainty in the final result, we use rule for subtraction. As x is equals to x2 minus x1, we have x2 is equals to 26.8 and x1 is equal to 10.5. 26.8 minus 10.5 gives x is equals to 16.3 centimeter. This is our measured value. What is the uncertainty in this measured value? According to the rule for addition and subtraction, absolute uncertainties are added. So we just add both uncertainties. Uncertainty in x1 is delta x1 and uncertainty in x2 is delta x2. x1 is 10.5 with uncertainty plus minus 0.1 centimeter, and x2 is equals to 26.8 with uncertainty in it plus minus 0.1 centimeters. So both uncertainties are added, plus minus delta x1 plus minus delta x2 are added, and we get total uncertainty in the measurement delta x is equal to plus minus 0.1 plus 0.1 centimeter, and finally we get delta x is equal to plus minus 0.2 centimeter. This is the uncertainty in final result, and we can write it as x plus minus delta x is equals to 16.3 plus minus 0.2 centimeter. We write our final result with uncertainty in it. Our final result is x plus minus delta x, where x is measured value and plus minus delta x is uncertainty in the final result. Here in this experiment, we subtracted both values and we applied the rule for subtraction, that is, add the both uncertainties. Similarly, when we do experiment and when we add the values to get the final measured value, we follow the same procedure and rule for addition, because rule for addition is same as rule for subtraction. So we will do the same procedure, and by adding the both uncertainties we will get uncertainty in the final result, where we add the measured values. But in this experiment we did subtraction and we calculated the uncertainty in final measurement. Same process can be done for adding the values. Rule for addition and subtraction. Let's solve another example. If d1 plus minus delta d1 is equals to 24.0 plus minus 0.1 centimeter, represents the internal diameter of a metal ring, and d2 plus minus delta d2 is equals to 30.0 plus minus 0.1 centimeter, represents the external diameter of a metal ring. Then find the thickness of a ring along with uncertainty in it. By the way, this is picture of diamond ring. This ring has some thickness T. So due to this, it has internal and external diameters. Its internal diameter d1 is 24.0 centimeters and uncertainty in it is plus minus 0.1 centimeters. And its external diameter is d2 is equals to 30.0 centimeters, and uncertainty in this diameter is plus minus 0.1 centimeter. Now we need to calculate the thickness of this metal ring and the uncertainty in this thickness. So let's calculate it. For calculating the thickness of this metal ring, we subtract d2 minus d1 and then we divide by 2. When we subtract both diameters d2 minus d1, it gives us thickness on both sides, but we need only the thickness. So we divide it by 2 to get thickness of the metal ring. T is equals to d2 minus d1 divided by 2. Putting the values, we get T is equals to 30.0 minus 24.0 divided by 2. We get T is equals to 3 centimeter. So thickness of this metal ring is 3 centimeter. Now we can apply rule of addition and subtractions to get the uncertainty in thickness. We know that when we subtract measured values, we add the uncertainties. Uncertainty in thickness is delta T is equals to plus minus delta D1, that is uncertainty in D1, plus delta D2, that is uncertainty in D2. By adding both uncertainties, we get delta T is equals to plus minus 0.2 centimeter. We write final answer with uncertainty. So our final measured value is T, thickness of this metal ring, plus minus delta T, uncertainty in this thickness, that is equals to 3 plus minus 0.2 centimeters. 3 is our measured value, that is thickness of this metal ring, and plus minus 2 is uncertainty in this measured value, that is delta t. So whenever we write final result, we write uncertainty with it in this form. Product and quotient rule. When we multiply or divide measured values in calculation, we add percentage uncertainties to calculate the uncertainty in final result. Don't be confused. In previous rule, product subtraction and addition rule, rule number A, that was for addition and subtraction rule. In that rule, we discussed that to calculate the uncertainty in final result, we add the absolute uncertainties. But here in product and quotient rule, when we multiply or divide values, we calculate uncertainty in final result by adding percentage uncertainties. Let's see an example. Calculate the resistance of a conductor if the measurement of voltage and current are 7.3 volt and 2.73 ampere. With the voltmeter of precision 0 0.1 volt, 0 0.1 volt is least count of the voltmeter, and ammeter of the precision of 0.05 ampere, 0.05 is least count of the ammeter. Solution. Voltage is equals to 7.3 plus minus 0 0.1 volt. As we discussed in previous slide that we write final answer with uncertainty in that measured value. So here 7.3 is measured value of voltage and plus minus zero point 0.1 is absolute uncertainty in this measured value. Current I is equals to 2.73 plus minus 0.05 ampere. Here 2.73 is measured value of current and plus minus 0.05 ampere is absolute uncertainty in this measurement. From question, we have to calculate the resistance in a conductor. By using Ohm's law, V is equals to IR and R is equals to V upon I. Putting the values of V and I, we get R is equals to 7.3 divided by 2.73 is equals to 2.7 ohm. 2.7 ohm is measured value of resistance, but we know that for writing the final answer, we write measured value with uncertainty in that. So now we have to calculate absolute uncertainty delta R. Here we will apply the product and quotient rule. We know that according to this rule, when values are multiplied or divided, we add the percentage uncertainties. Here R is equals to V divided by I. So V is divided by I. So due to this, we apply product of quotient. Product and quotient rule. Total uncertainty, percentage uncertainty in R is equals to percentage uncertainty in V plus percentage uncertainty in I. So for adding the percentage uncertainties, we need to calculate percentage uncertainty in V and percentage uncertainty in I. By using the formula, we get the percentage uncertainty in V is equals to 0 0.1 divided by 7.3 multiplied by 100 divided by 100 is equals to 1.37%. Here 0 0.1 is least count, 7.3 is measured value, and when it is multiplied by 100%, we get the total percentage uncertainty NV, that is 1.37%. Rounding off 1.37%, we get 1%. The percentage uncertainty in I is equals to 0.05 ampere divided by 2.73 ampere multiplied by 100%. Here 0.05 is least count of the ammeter and 2.73 is measured value of current, and by multiplying it with 100%, we get the percentage uncertainty in I is equals to 1.83%, and by rounding off this number, we get total percentage uncertainty in I is equals to 2%. And when we add these two percentage uncertainties, we get percentage uncertainty in R, that is equals to 1% plus 2%, and the total percentage uncertainty in R is equals to 3%. Now we know the total percentage uncertainty in R, but for writing the final answer, we need absolute uncertainty in R. To calculate the absolute uncertainty in R, we use the formula percentage uncertainty in R is equals to absolute uncertainty in R divided by measured value multiplied by 100%. This is the formula of percentage uncertainty. By rearranging this formula, we get absolute uncertainty in R is equals to plus minus percentage uncertainty in R multiplied by measured value divided by 100. By putting the values, we get absolute uncertainty in R is equals to plus minus 3 multiplied by 2.7 ohm divided by 100, and finally we get absolute uncertainty in R, that is equals to delta R is equals to plus minus 0.08 ohms. Now we have absolute uncertainty in R and measured value in R. So we can write the final answer as R plus minus delta R is equals to 2.7 plus minus 0.08 ohms. Actually here R is measured value and plus minus delta R is absolute uncertainty in resistance. Next rule is power of a quantity. For power factor, multiply the percentage uncertainty by that factor. For example, we have x is equals to y to the power r. So for calculating the percentage uncertainty in x, we multiply power factor r by percentage uncertainty in y. Let's solve a question. Calculate the uncertainty in volume of a sphere of radius 2.25 cm as measured with the vernier calipers of least count 0.01 cm. Solution: as the measured value of radius r of a sphere is r is equals to 2.25 cm and absolute uncertainty, that is least count, is equals to plus minus 0.01 centimeter. This is delta r, because we know that absolute uncertainty or least count is represented by delta r for radius, and we write the measured value with r is equals to 2.25 plus minus 0.01 centimeter. R is our final value and our measured value is 2.25, and absolute uncertainty in this value is plus minus 0.01 centimeter. In question, we need to calculate volume of a sphere. Formula of volume of a sphere is equals to V is equals to 4 upon 3 pi r cube, and in this formula we have power factor 3. So we have to use the rule power of a quantity here. For that, we will multiply the percentage uncertainty by that power factor. First of all, calculate the measured value of volume by just putting the value of pi and r. In this formula, V is equals to 4 divided by 3 pi r cube. By putting the values, we get volume of a sphere is equals to 4 divided by 3 multiplied by 3.142, that is the value of pi, multiplied by 2.23 centimeter whole cube. 2.23 is 2.25 is radius, measured value of radius. By solving, we get V is equals to 47.689 centimeter cube. Now we have the measured value of volume. For calculating the percentage uncertainty in volume, multiply the power factor with percentage uncertainty in radius. For that, we need to calculate the percentage uncertainty in radius, that is equals to least count divided by measured value multiplied by 100%. Least count is 0.01 divided by measured value, that is 2.25 centimeter multiplied by 100%, and we get the percentage uncertainty in R is equals to 0.4 centimeter. Now we can multiply this percentage uncertainty in R with power factor 3 to get the percentage uncertainty in volume. And finally we get percentage uncertainty in volume is equals to 1.2%. By applying the power of a quantity rule, we got the percentage uncertainty in volume. But we note that we write our final answer with measured value plus minus the uncertainty in this value, measured value. The measured value of volume is 47.689 centimeter cube, but we don't have the absolute uncertainty delta V. So for calculating absolute uncertainty in V, we have formula absolute uncertainty in V is equals to plus minus percentage uncertainty in V multiplied by measured value of V divided by 100. We just rearrange the formula of percentage uncertainty to calculate the absolute uncertainty. Now putting the values, we get absolute uncertainty in V is equals to plus minus 1.2 multiplied by 47.7 centimeter cube divided by 100. And finally we get absolute uncertainty in V delta V is equals to 0.6 plus minus 0.6 centimeter cube. And we know that we write final answer with V is equals to measured value plus minus absolute uncertainty in V. So V is equals to 47.7 plus minus delta V 0.6 centimeter cube. Here 47.7 is measured value in volume and zero point 0.6 plus minus zero point 0.6 is absolute uncertainty in this measured value. Uncertainty in average values of measurements. To find uncertainty in mean value, we follow these steps. Step number 1, find the average value of measured values. Step number 2, find deviation of each measured value from the average value. Step number 3, the mean deviation is the uncertainty in the measured value. The mean deviation value is equal to the uncertainty in mean value. Let's solve an example. Measured value of an experiment are x1 is equals to 1.50 centimeter, x2 is equals to 1.51 centimeter, and x3 is equals to 1.52 centimeter. Find the uncertainty and average values of this experiment. By using step number 1, average value are average value is x is equals to x1 plus x2 plus x3 divided by 3, because total number of measured values are 3, so we add them and divide them by total number 3. By putting the values, we get average value is equals to 1.50 plus 1.51 plus 1.52 divided by 3, and then we get mean value is equals to 1.51 centimeter. Now by using step number 2, deviation of each quantity can be determined. Deviation in quantity x1, delta x1 is equals to mean value minus measured value of x1. So delta x1 is equals to mean or average value minus measured value of x1. Mean value is 1.51 and measured value of x1 is 1.50. By putting the values, we get delta x1, deviation in x1 is equals to 0.01 centimeter. Similarly, we can calculate the deviation in x2 and deviation in x3, and by putting the values we get delta x2, deviation in x2 is equals to 0 and deviation in x3 is equals to delta x3 is equals to 0.01 centimeter. Now by using this step number 3, the mean deviation is equals to delta x1 plus delta x2 plus delta x3 divided by 3. By putting the values, we get mean deviation, that is the uncertainty in mean value is equals to 0.0067 centimeter. By rounding off, we get mean deviation uncertainty in mean deviation is equals to 0.007 centimeter. So by using these 3 steps, we can calculate the uncertainty in average values of any measurement. Uncertainty in timing experiment. The time period of a simple pendulum or any other vibrating body can be found by the formula time period is equals to T is equals to total time of all vibrations divided by total number of vibrations. and the absolute uncertainty in time period is equals to delta t is equals to least count of stopwatch divided by total number of vibrations. Let's see an example. Calculate the time period and uncertainty in time period of a pendulum if it completes its 30 vibrations in 54.6 seconds, which is calculated by a stopwatch of at least count of zero point 0.1 second. Solution. We know that time period t is equals to total time of all vibrations divided by total number of vibrations. By putting the values, we get time period is equals to 54.6 divided by 30, which is equals to 1.82 seconds. Now for calculating the absolute uncertainty in time period, we use the formula and put the values, and we get absolute uncertainty in time period is equals to delta t is equals to 0.1 second divided by 30, and that is equals to 0.003 seconds. We write final answer with absolute uncertainty, and final answer is t is equals to 1.82 measured value of time period plus minus 0.003, that is delta t absolute uncertainty in time period. So t is equals to 1.82 plus minus 0.003 seconds. Thank you. Take care.